Have you ever stopped to think about what a perfect 3D shape would even look like? A shape that's so symmetrical, so regular, it feels like it has to be a fundamental building block of the universe. Well, shapes like that do exist. But here's the crazy part. There are only 5 of them. That's it. Let's dive into this little mathematical mystery. Here they are, the Platonic solids. These things have fascinated people for literally thousands of years, all the way back to ancient Greece. They're part of this incredibly exclusive club. And in this explainer, we're going to figure out exactly why the guest list is so short. So that's the big question, right? Why is it just 5? Why can't we just cook up a 6th one or a 7th? I mean, it feels like there should be endless possibilities. But mathematics puts its foot down and says nope. So let's put on our detective hats and find out why. To solve this, first, we need to know the rules for getting into the club. A Platonic solid has to follow 2 very strict rules. First, every single face has to be the exact same regular polygon. Think perfect squares, perfect triangles, that kind of thing. And second, every single corner or vertex has to be identical with the exact same number of faces meeting there. And you know what? These 2 rules are the only clues we need. If we just think through what they mean, we can logically prove why only 5 shapes ever make the cut. So let's take a look at our evidence, starting with clue number 1. So this first rule means our building blocks have to be perfect. We can only use shapes like equilateral triangles, squares, or regular pentagons, where every side is the same length and every angle is the same. No weird, lopsided, or stretched out shapes are allowed. Now, for the second clue. And honestly, this is the big one. This is the rule that cracks the whole case wide open. The angles of the faces that meet up at any single corner, they have to add up to less than 360 degrees. So why is that so important? Well, think about it like you're tiling a floor. If the angles add up to exactly 360 degrees, you don't get a corner. You just get a flat surface. There's no room to fold. You need to have some angular space left over to be able to bend the shape up into the 3rd dimension and actually form a point. All right, we've got our rules, so the investigation begins. Let's start with our first potential building block, the equilateral triangle. Each of its corners has an angle of exactly 60 degrees. So how many can we fit around a single point without hitting that 360-degree ceiling? Verdict! Success! Let's try it. 3 triangles? That's 180 degrees. Plenty of room to fold. 4 triangles? That's 240 degrees. Still works. 5 triangles? That gives us 300 degrees. That works too. But what about 6 triangles? That's 360 degrees on the dot. It lies flat. So, right away, triangles give us 3 possible solids. Okay, let's move on to our next suspect, the square. Each corner is a nice, perfect 90-degree angle. Let's apply that less than 360 rule and see what happens. And what do we find? Well, 3 squares at a corner add up to 270 degrees. That works. You can definitely fold that into a corner. But if you try to add a 4th square, that's 90 times 4, exactly 360 degrees. It lies perfectly flat. So squares give us just 1 possible solid. Okay, continuing our investigation, we get to the regular pentagon. Now, the angles are getting a lot bigger. Each corner of a regular pentagon is 108 degrees. This is going to be a pretty tight squeeze. And look at that. 3 pentagons together add up to 324 degrees. It's less than 360, so it just works. But there's no way you're fitting a 4th one in there. That would jump way over the limit. So the pentagon gives us 1 last possible solid. And this brings us to the end of the road. I mean, what about hexagons or polygons with even more sides? Let's see if any of them can pass the test. The verdict? Impossible. And this is actually a perfect illustration of our rule. Each corner of a hexagon is 120 degrees. So if you take the minimum number you need to form a vertex, which is 3, that's 3 times 120, 360 degrees exactly. They can't form a corner. They can only tile a flat surface, kind of like a honeycomb. And since any polygon with more sides has even larger angles, they're all out. So let's just look at the final tally. We found out that triangles can form a corner in 3 different ways. Squares can do it in only 1 way. And pentagons can also do it in only 1 way. And that's it. We've run out of shapes. 3 + 1 + 1 = 5. Our investigation proves there can only ever be 5 possibilities. So the case is officially closed. The math just doesn't lie.
Now, let's get formally introduced to the 5 members of this very exclusive club, the Platonic solids.
First up, we've got the simplest one, the tetrahedron. It's built from just 4 triangular faces, and it's the result of that very first successful test we ran, putting 3 triangles together at every corner.
Next is the one we all know and love, the hexahedron, which we just call the cube. It's made of 6 square faces. This is our one and only solid that can be built from squares, with 3 of them meeting at each point.
And here's our second solid made from triangles, the octahedron. This one has 8 faces, and it's what you get when you join 4 triangles together at every single corner. Say hello to the dodecahedron, our lone soldier from the pentagon family. It's built from 12 pentagon faces, with 3 meeting at each vertex, just barely squeaking under that 360-degree limit.
And finally, the most complex of the bunch, the icosahedron. This is our third and final shape made from triangles. It has a whopping 20 faces, and it's formed by packing the absolute maximum possible number of triangles, 5 of them, around each and every corner. And there you have it, the 5 and only 5 perfect solids, all proven by just a couple of simple rules. It really makes you wonder, doesn't it? What other amazing universal truths are just hiding out there in the simple language of math, waiting for us to find them?